take a look at question 3 from 2017. So this is from the 2017 paper last year, November, and this is for the Aqueous Systems External Standard. Question 3 is all about titration curves, and it's been that way for the last 3 years, so you can expect question 3 in 2018 to be about a titration curve. The other thing I can say as well is that in 2017 they dealt with a weak acid and a strong base titration curve. In 2016, they dealt with a weak base and a strong acid titration. And then in 2015, they went back to a weak acid and a strong base. So if you had to make a prediction for 2018, it could be a weak base and a strong acid titration. But know these two types of curves. And before I even get into answering anything specifically for the question, we should just label as many of the parts of this titration curve as we can. So the first thing here is that we have an initial low pH, and this is from the weak acid alone. So initially in your beaker, before you add any of the strong base, you have just a weak acid. So the reaction that's actually happening here is it's ethanoic acid plus water, and it's a weak acid, so you have an equilibrium, and you'll get the ethanoate CH3COO minus plus the H3O plus ions. Now, it's this concentration of H3O plus ions that accounts for the pH, which is slightly acidic. Then there is an initial bump or increase in the pH, and that's due to the addition of the strong base. So the strong base is added, and there's a little jump in the curve as it detects that increase in pH. But then you have a flattening out of the curve, and this is the buffer zone. So this is your buffer zone. And the buffer zone is possible because of the fact that when you are halfway along the buffer zone, you're at the midpoint. And so this is called midpoint of the titration curve. And the midpoint is where you have effectively created a buffer, because what you've done is you've taken your acid and you've half neutralized it with your strong base. And if you half neutralize your acid and half of it is now in its conjugate base form, well, you then have a situation where you have a buffer system because you have equal amounts of the conjugate base and the weak acid. So if these amounts are roughly equal, approximately equal, this little line is abbreviation for approximately, in case you didn't know. And if you have equal amounts of those two components, you have a buffer system, and that's why it buffers against the addition of any strong base for that period of time. But then we have a point where the graph suddenly shoots upwards, so this is the point of inflection. So the point of inflection represents where the buffer system is broken. So the buffer system is now effectively broken, and so it can't buffer anymore, and then the pH rises sharply. If you draw a straight line across here and here, then halfway up that vertical section, you have what's known as the equivalence pH. So the equivalence pH. And the equivalence pH for a weak acid and a strong base titration, remember, is always going to be greater than 7. And you can see there, if you read it off your graph, the equivalence pH looks to be around 9 from this example. And this is important then if we are choosing the correct indicator, because the rule of thumb with choosing the correct indicator to detect the equivalence pH is that the indicator's pKa must be plus or minus 1 pH unit above or below the pH at equivalence. So if we've determined here from our graph that our pH at equivalence is 9, and we have an indicator here which can operate from 8 up to 10, so 1 pH unit above and below, then we will clearly cover that equivalence point pH. And so phenolphthalein is the correct indicator for this titration. Some students will just memorize phenolphthalein goes with the weak acid strong base titration, but that's the theory behind it. And all you have to do is tick that box. So I'd imagine there would have been an achieved mark going for that. The methyl yellow one is more appropriate for the titration of a weak base and a strong acid, so just remember that. And the bromo creosol purple is not really relevant unless you're giving some other examples. Okay, so we've basically interpreted everything that's going on with our titration curve. When you get up to this point here where it maxes out, and that to me looks like a pH of 14, which is very high, but that's the maximum pH of your strong base alone. So there's no more weak acid anymore. There's no more buffering capability. It's just strong base. So now that we've totally stripped down the information in that curve, let's take a look at what other questions they ask us in 2017. Now I'm going to delete some of these things here because otherwise there's too much to look at. So I'm just going to pause this and delete some components. Okay, so what I've done is I have moved some of the question over here now, and we're going to take a look at part B. Now, part B is referring to the ethanoic acid solution having a pH of 2.77 to begin with, before any sodium hydroxide is added. So this is this pH that we're referring to here. So we're given a value for it as 2.77. And then what we want to do is we want to show by calculation that the concentration of ethanoic acid at this point is that value right there. So the key thing is to understand the chemistry that's taking place, and that's a bit of an understatement. But we only have ethanoic acid present in our beaker. So the reaction which is accounting for this pH has to be the equilibrium that the ethanoic acid establishes as it reacts with water. So we've written this already. Ethanoate plus H3O plus ions. And then it's just a good old Ka expression for that. So ethanoate on the top, and the hydronium ions, and then the concentration of the ethanoic acid on the bottom. I can already see I'm going to run out of space here. So we want to show that the pH is 2.77. So the Ka we've been given in the question. So we have that value. We can run our assumption here because there is no strong base added, so it's just a pure weak acid system. So we can run our usual assumption that these two concentrations are equal, in which case the Ka can now be abbreviated to Ka equals concentration of hydronium ions squared over the concentration of the ethanoic acid. So that should be squared. If you do that, the concentration of the hydronium ions we can figure out from the pH of 2.77, because 10 to the negative pH, or 10 to the negative 2.77, will give you a concentration of hydronium ions of, just check this from before, so I did this on paper, that works out to be 1.698 by 10 to the negative 3. So I'm just going to free up a bit more space for myself here. So I just deleted the question, so probably be handy to have the question in front of you as I go through this, but the working is still the same. So this is B part 1. Okay, and we've worked our way through. We said that the pH of this solution, which is 2.77, is going to be due to the weak acid alone dissociating. And we worked out the concentration of the hydronium ions from that pH of 2.77, and that number ended up being 1.698 by 10 to the negative 3. So that's the concentration of the H3O plus, just to make it a bit clearer for you. And so we know the value of H3O plus. We know the value of the Ka from up here. So we should be able to work out the concentration of the ethanoic acid. So let's do that. So if we move over here now to give us some space, we're going to rewrite our expression. The Ka is 1.74 by 10 to the negative 5. Okay. Then if we take that value and above it, we put the concentration of the hydronium ions, which we figured out earlier, and we square that number. So we're just doing this calculation here. And we took the Ka across and we moved the concentration of ethanoic acid over there. So that's equal to the concentration of the ethanoic acid. All right. And so if we perform that calculation, we'll get a concentration for the ethanoic acid of 0.166 moles per liter. And so what's nice about this question is they actually gave you that value in the question, so you're just working towards confirming that that is the right answer. So that's how you do question 3b, so part 1, and let's take a look at part 2. Okay, so B part 2 is definitely the trickiest part of this question in 2017. And let's take a look at what they're asking. So they're asking to calculate the pH of the solution after 10 mils of the strong base has been added to the 20 mils of ethanoic acid solution. So let's just try and visualize what we're doing here. So we have a burette, terribly drawn, And the burette is dropping sodium hydroxide into a conical flask. Inside the conical flask, to begin with, we had 20 mils of the ethanoic acid. So that's CH3COOH. And the concentration of the ethanoic acid, we don't know, well, we do know actually from B part 1. So that was 0.166 moles per liter. So we know the concentration of the ethanoic acid in 20 mils, but you see what we've done is we've added 10 mils of sodium hydroxide to it. And so if you see two solutions being added together, the alarm bell must go off in your head that a dilution factor is taking place here. So there's a dilution factor to consider. Okay. And the concentration of the sodium hydroxide there is 0.112 moles per liter. So you can see that in the question right there. Okay. And so what we want to talk about is basically the point in the graph we're referring to is when we've added 10 mils of sodium hydroxide, we just use this blue color to try and identify what I'm talking about. So at 10 mils of the sodium hydroxide, we're talking about this pH here. So without actually doing the calculation, you can see that it's about 4.8. All right, that pH is about 4.8. And we have to show by calculation, though, so we can't just get away with reading it off your graph. But be aware that you could have done that to get a guideline of whether you're on the right track. So we know we should be getting a pH of about 4.80. This means approximately, by the way, in case you didn't know that. So approximately. Okay. So we're aiming for 4.8 roughly. Now, what we have going on here